about capacitors and the electric field of a capacitor, but we're going to take a look at a little bit more at what some things that they do. The main purpose of a capacitor is to store electrical energy. The word capacitor is the same root word as the word capacity, how much something can hold, and they store electrical energy. They're used in a lot of electronics when a sort of a burst of energy is used, and I'll talk a little bit about some things where that happens in a bit. Excuse me. Typically what happens is that you have these two electrical plates, and then they're hooked up to a battery, which I can't really draw very well, but battery. When we do circuits, we'll learn some symbol that means battery, but the two plates of the capacitor are hooked up to a battery, which enforces some kind of potential difference between the upper and lower plates. And because there is this potential difference, the electrons flow off of one plate onto the other, and they wind up giving one plate a negative charge and the other plate a positive charge. Okay. Then the capacitor is cut off from the battery, and then you have these two plates that have a charge on them because there's nowhere else for the charge to go, and therefore there is some kind of potential difference between them. And then once they have a given charge, they're often moved closer together or further apart, or they have something put in between them to change what the potential difference might be, and what the capacitance of the capacitor is. The ratio of the charge to the potential difference is called the capacitance. Capacitance C is equal to Q over V. And the unit for capacitance, it's a charge, coulombs, over a potential difference, volts, and 1 coulomb per volt is called 1 farad, named after Faraday, who was a famous scientist that did a lot of work with electricity and magnetism. It's capital F, and typically, and Q is the charge on one plate, so the top plate will have charge plus Q, the bottom plate will have charge minus Q, but just the positive value is what goes into this equation. Values of capacitance are typically somewhere from picofarads to microfarads. Pico is 10 to the minus 12th, and micro, as you should know, is 10 to the minus 6th. So that's what capacitances typically are. Now, before we learned that the electric field of a capacitor is a sigma over epsilon naught. And remember, sigma was a charge per area. So the electric field is Q over area times epsilon naught. Area is the area of the plate. We know a change in potential is a minus E field times a delta S. So if we plug in this for the E field, we get that the change in potential of our capacitor, the potential difference between the two plates of the capacitor, is Q minus, or Q over A epsilon naught times that delta S negative. Right? And therefore capacitance, following up with this equation, is equal to Q over, technically this is a potential difference, minus Q delta S over A epsilon naught. Q's go away. And that leaves us with epsilon naught times area over delta S. In this case, the delta S is usually just replaced with a distance, because a displacement in the direction of the electric field is just, straight down, and so typically they just give it in terms of that distance d, the distance between the plates. So this is the area of a plate, and this is the distance between plates.